Every decision you have ever made, what you ate this morning, who you called last week, whether you turned left or right, happened once. You made a choice. The other option disappeared. Or did it? There is a serious, peer-reviewed, mathematically rigorous branch of physics that says the other option did not disappear. It happened. In a universe running parallel to yours, right now, a version of you made the other choice. And that universe is just as real as this one. This is not science fiction. This is not a metaphor. This is one of the most debated and genuinely unsettled questions in all of modern physics. And here is the thing that should stop you cold. The physicists who believe this, and there are many, do not believe it because it sounds exciting. They believe it because the math of quantum mechanics, taken seriously, appears to demand it. The question is not whether the idea is wild. The question is whether the universe cares that the idea is wild. And the answer, as we are going to show you over the next 70 minutes, is deeply, uncomfortably unclear. Chapter 1. The problem that started everything. To understand why anyone would propose that multiple universes exist, you first need to understand the specific, very strange problem in physics that made the idea necessary. It starts with a question about light. In the early 1800s, a British scientist named Thomas Young wanted to know whether light was a wave or a particle. He did something simple. He took a barrier with two narrow slits cut into it, shone light through it, and looked at the pattern it made on a screen behind. If light was made of particles, like tiny bullets, you would expect two bright lines on the screen, one from each slit. That is not what he saw. He saw a pattern of many alternating bright and dark bands spreading across the entire screen. An interference pattern, the kind of pattern you get when two waves collide and either add together or cancel each other out. Light, it turned out, behaved like a wave. Fine, that was 1801. Problem apparently solved. Then, a century later, everything broke again. Physicists discovered that light also came in discrete packets, individual chunks called photons, particles. So which was it? A wave or a particle? The answer that quantum mechanics eventually gave was both and neither, depending on when you look. Here is where it gets strange in a very specific, very non-metaphorical way. When you fire photons through the double slit one at a time, so only a single particle is in the apparatus at any moment, you still get the interference pattern. Each photon, individually, spreads out and interferes with itself, as if each photon went through both slits simultaneously, as if the photon was, in some sense, in two places at once. Then you do something different. You place a detector at the slits to observe which slit the photon actually goes through. The moment you do that, the moment you obtain information about the photon's path, the interference pattern vanishes. Now you get two lines. Particle behavior. The act of observation destroyed the wave behavior. This is not a flaw in the detector. It is not a disturbance caused by the measurement equipment. This is a fundamental feature of quantum mechanics, and it forced physicists into a question that has never been fully resolved. what is actually happening to the photon before you look. Chapter 2. Schrödinger's Real Problem. In 1935, the Austrian physicist Erwin Schrödinger was deeply frustrated, not with experiments, with the interpretation of quantum mechanics that was becoming the standard. It was called the Copenhagen interpretation, championed primarily by Niels Bohr. The Copenhagen view said, before measurement, a quantum system exists in a superposition, a combination of all possible states simultaneously. When you measure it, the superposition collapses. One outcome appears, the others vanish. Schrödinger found this profoundly unsatisfying. So he constructed a thought experiment specifically designed to reveal how absurd the collapse idea becomes when you apply it to large, everyday objects. You probably know the setup: a cat in a box, a radioactive atom, a poison mechanism. The atom has a 50% chance of decaying in 1 hour. If it decays, the poison is released. The cat dies. If it does not, the cat lives. According to Copenhagen, before you open the box, the atom is in superposition, both decayed and not decayed simultaneously, which means, following the logic strictly, the cat is both dead and alive simultaneously. Schrödinger did not propose this as a cute puzzle. He proposed it as a reductio ad absurdum, a demonstration that the Copenhagen interpretation must be missing something. A cat cannot be simultaneously dead and alive in any meaningful physical sense. Something must decide the outcome before you open the box. The Copenhagen response, essentially, was the question of what happens before measurement is not a physical question. Stop asking it. Schrödinger was not satisfied. Neither, it turned out, was a Princeton graduate student named Hugh Everett. Chapter 3. The student who refused to accept the answer. In 1957, Hugh Everett III submitted his doctoral thesis at Princeton. It was one of the most radical documents in the history of physics, and it was largely ignored for almost 20 years. Everett's starting point was a specific discomfort with the collapse postulate in standard quantum mechanics. The collapse, the idea that a superposition suddenly and discontinuously jumps to a single outcome upon measurement, was, to Everett, a klug, an awkward add-on to an otherwise mathematically clean theory. Here was his key observation. The Schrödinger equation, which governs how quantum systems evolve over time, is perfectly smooth and deterministic. It does not predict collapse. It does not predict superpositions vanishing. What the Schrödinger equation actually predicts, if you apply it without restriction, is that superpositions keep spreading. They grow, they entangle, they encompass everything they interact with, including the measuring device, including the scientist doing the measuring, including the room, including the universe. Everett's proposal was, what if you just trust the math? What if the Schrödinger equation is telling the truth and there is no collapse at all? What actually happens in Everett's framework is that when a measurement occurs, the universe does not pick one outcome and discard the others. It branches. Every possible outcome occurs. In one branch, the cat is dead. In another branch, the cat is alive. Both branches are equally real. Both contain a version of the scientist who opened the box. Both contain a version of you reading about the experiment. Each branch is unaware of the others because after branching they cannot interact. They have decohered, become, for all practical purposes, separate universes. This is the many worlds interpretation. Everett's thesis advisor, John Wheeler, found it compelling but politically sensitive. He advised Everett to tone it down. Everett shortened the thesis. He removed the phrase "many worlds" entirely from the submitted version. Bohr's group in Copenhagen was dismissive, and Everett, disillusioned by the reception, left academic physics and spent his career doing military operations research. He died in 1982 at age 51, never knowing that his idea would eventually become one of the most seriously discussed interpretations in theoretical physics. Chapter 4. What decoherence actually explains. For 2 decades after Everett's thesis, many worlds was treated as a curiosity at best. The core criticism was simple. If all these branches exist, why don't we see them? Why does every experiment yield one result? Not many. Everett's original answer, that the branches cannot interact after splitting, was philosophically suggestive but physically vague. Then, in the 1970s and 1980s, physicists developed a rigorous account of something called decoherence, and it changed the conversation. Decoherence is what happens when a quantum system, a particle, an atom, a superposition, interacts with its environment. When a quantum object interacts with even a single air molecule, information about its state leaks into the environment. That information rapidly spreads to trillions of surrounding particles. Once that happens, the different components of the superposition can no longer interfere with each other. They behave, to all detectable measurement, as if they are completely separate. The key word is "as if." Decoherence does not destroy the other branches. It makes them inaccessible. It makes them informationally invisible to each other. German physicist H. Dieter Zeh was among the first to develop this framework rigorously, beginning in 1970, though his early papers were also initially resisted. What decoherence provided for many worlds was a physical mechanism for why we perceive a single outcome. When you measure a quantum system, your measuring device, a macroscopic object containing roughly 10 to the power of 23 atoms, immediately entangles with the quantum state. Decoherence kicks in within femtoseconds. The branches separate so fast and so completely that no physical process you could perform would ever bring them back together. From the inside of any given branch, it looks exactly like collapse occurred. The other branches are there in the mathematics, but they are effectively gone from your experience. This was a significant advance, but it also opened a new problem, one that is arguably even harder than the original. Chapter 5. The probability problem. No one has fully solved here is a question that sounds simple, but is genuinely devastating for many worlds. If every quantum measurement causes a branch where every outcome occurs, if every possibility is real, then what does it mean to say one outcome is more probable than another? In standard quantum mechanics, the probability of each outcome is given by a rule called the Born rule. Named after physicist Max Born, it says, "The probability of a particular outcome is the square of the amplitude of the corresponding component of the quantum wave function." This rule works extraordinarily well. Experimental predictions based on it are accurate to more decimal places than almost any other measurement in science. But the Born rule is inserted into standard quantum mechanics by hand. It is a postulate, an assumption. It is not derived from anything more fundamental. In many worlds, the situation is potentially worse. If all outcomes happen and each branch is equally real, then in what sense is one outcome more probable than another? Consider an experiment where quantum mechanics predicts a 75% chance of outcome A and a 25% chance of outcome B. After measurement, both branches exist. The branch where outcome A occurred is real. The branch where outcome B occurred is also real. Both branches contain a real person who observed a real result. Why should either person assign a probability of 75% to anything? This is called the probability problem, or the Born rule problem, in many worlds. It has occupied serious physicists for decades. In 2007, Oxford physicist David Deutsch proposed a solution using a branch of mathematics called decision theory. His argument, later refined by colleagues including David Wallace, was roughly this. A rational agent, knowing they will branch, can still assign meaningful probabilities to outcomes based on the structure of the quantum state. Specifically, they should act as if the probability is given by the Born rule, because any other strategy is incoherent from a decision-making standpoint. The argument is subtle and contested. Some philosophers of physics find it genuinely compelling. Others argue it smuggles the Born rule back in through the back door, rather than deriving it. This debate is ongoing, published in serious journals, and not close to resolution. Chapter 6. The Landscape of Other Proposals. Many worlds is not the only response to the quantum measurement problem. It is important to understand this because the existence of competing interpretations tells you something crucial. Physicists are not arguing about which interpretation is true because there is obvious evidence for one of them. They are arguing because the evidence so far does not cleanly distinguish between them. The oldest competitor is Copenhagen, which we have already discussed. Its modern form is sometimes called shut up and calculate, a phrase attributed, possibly unfairly, to physicist David Mermin. The idea is use quantum mechanics to predict experimental outcomes and do not ask what is really happening between measurements. That question has no operational meaning. This position is pragmatically powerful. It is also philosophically uncomfortable for anyone who thinks physics should describe reality, not just predict measurement outcomes. A second major alternative is called pilot wave theory, or Bohmian mechanics. Developed by Louis de Broglie in the 1920s and independently revived by David Bohm in 1952, this interpretation says particles have definite positions at all times. They are guided by a real wave, the pilot wave, that is not directly observable but determines where particles go. In this picture, there is no superposition in the way Copenhagen describes. No collapse. Particles always have definite trajectories. The interference pattern in the double-slit experiment is explained by the pilot wave pushing particles into particular regions. Pilot wave theory makes the exact same predictions as standard quantum mechanics, but it requires the wave to be non-local, meaning information about the entire configuration of the universe is instantaneously available everywhere in determining how any single particle moves. This non-locality is deeply uncomfortable for physicists who want theories compatible with relativity. Extending Bohmian mechanics to quantum field theory, the framework underlying particle physics, has proven extremely difficult. A third alternative is called objective collapse, or GRW theory, named after physicists Girardi, Rimini and Weber, who formalized it in 1986. The idea collapse is real and physical. It is not caused by measurement. It happens spontaneously at random at a very low rate. For a single particle, the collapse rate is so low that it almost never matters. But for a macroscopic object containing many particles, collapses happen constantly, effectively always. This prevents superpositions from ever becoming macroscopic. No cats can ever be in two states at once. GRW is testable in principle. If collapse is physical, it should produce a tiny but detectable amount of energy. Radiation released when the wave function localizes. Experiments searching for this radiation are ongoing. So far, they have not found it at the predicted rate, which places constraints on the collapse parameters. Each of these interpretations preserves the mathematical predictions of quantum mechanics. Each gives a radically different account of what is actually happening in reality, and the experiments done so far cannot tell them apart. Chapter 7. The multiverse is not one thing. Here is a distinction that most popular discussions completely miss. When physicists talk about a multiverse, they are not all talking about the same thing. There are at least 4 distinct concepts that get called a multiverse, and they come from completely different areas of physics. Conflating them creates enormous confusion. The first is the quantum multiverse, the many worlds picture from Everett. Branches of the wave function, parallel versions of events. These are the worlds that split every time a quantum measurement occurs. The second is the inflationary multiverse. This comes from cosmology, not quantum mechanics. The leading theory of the early universe says it underwent a period of extraordinarily rapid expansion called inflation. Inflation is driven by a field, the inflaton field, and the physics of that field suggests that inflation, once started, never fully stops globally. Different regions of space stop inflating at different times. Each such region becomes a universe unto itself, a bubble universe. These bubble universes can have different physical properties because the fields that determine things like the mass of the electron or the strength of gravity can settle into different configurations in each bubble. There could be bubble universes where the laws of physics are subtly or radically different from ours. We cannot see them. We cannot communicate with them. They are beyond our cosmic horizon. But the physics of inflation appears to make them a natural consequence of the theory. The third is the string theory landscape. String theory, the framework that attempts to unify quantum mechanics and general relativity, allows for an enormous number of possible configurations of extra dimensions and fields. The number is usually estimated at 10 to the power of 500. Each configuration corresponds to a possible set of physical laws, a possible universe. The question of whether our universe's particular laws are special or simply one of an astronomical number of possibilities is one of the deepest open problems in theoretical physics. The fourth is the mathematical multiverse. Proposed by MIT cosmologist Max Tegmark, this is the most radical. Every mathematically consistent structure exists as a physical reality somewhere. Not just universes with different physical constants, but universes with different fundamental laws, different dimensions, different geometries. In this view, the question, why does anything exist, has a clean answer. Everything mathematically possible does exist. These four concepts are distinct. The evidence for each of them is different in kind and in strength. And it is a mistake to treat them as a single idea called the multiverse with a single verdict. Chapter 8. The inflationary multiverse and what might test it. Of the four types of multiverse, the inflationary version is the one closest to mainstream cosmology. Inflation itself is supported by strong observational evidence. The cosmic microwave background, the afterglow of the Big Bang, mapped in exquisite detail by satellites including WMAP and Planck, shows a pattern of temperature fluctuations that inflation predicts with remarkable precision. The flatness of space, the uniformity of temperature across regions of the sky that should never have been in contact. Inflation explains both. But here is the issue. The specific version of inflation that leads to eternal inflation and bubble universes is not directly tested by those observations. It is a consequence of the mathematics, not a direct measurement. Now, can we ever detect another bubble universe? The short answer is possibly if one collided with ours. In the eternal inflation picture, bubble universes are constantly forming and expanding. The boundaries between bubbles move outward at nearly the speed of light. If two bubbles collide, the collision would leave a specific, calculable imprint on the cosmic microwave background, a circular patch with specific temperature and polarization properties. Physicists Matthew Johnson and Hiranya Paris, among others, have performed searches for these signatures. As of the current state of the field, no confirmed bubble collision signatures have been found. But the search is not over. Future experiments with higher sensitivity and polarization, such as the Simons Observatory and CMB-S4, both under development, may provide tighter constraints, or in principle, a detection. The inflationary multiverse is not unfalsifiable in principle. It has not been confirmed in practice. Chapter 9. The Anthropic Principle and Why It Is Controversial. There is a line of argument in multiverse physics that physicists find either genuinely powerful or deeply troubling, depending on who you ask. It is called the anthropic principle. The basic observation is this: The physical constants of our universe, the strength of gravity, the mass of the electron, the cosmological constant, appear finely tuned to allow complex structures, chemistry and life to exist. Change the strength of gravity by a small fraction. Stars cannot form. Change the cosmological constant, the energy density of empty space, by even a tiny amount. Galaxies do not form, or the universe expands so fast that matter cannot clump together at all. The cosmological constant problem is, in fact, one of the worst fine-tuning problems in physics. The observed value is about 120 orders of magnitude, smaller than the value naively predicted by quantum field theory. In a universe with only one set of physical laws, this level of fine-tuning demands an explanation. One explanation: a designer set the constants. Another explanation: in a multiverse with many different regions having different physical constants, we necessarily find ourselves in a region where the constants permit our existence. We could not observe any other region because we could not exist there to do the observing. This is the anthropic argument for the multiverse. Steven Weinberg used a version of this argument in 1987 to make a quantitative prediction about the cosmological constant before it was measured. His prediction, based on anthropic reasoning in the context of a multiverse, was in the right ballpark of the later measured value. This is cited as a genuine success of anthropic reasoning. Critics, including physicists like Paul Steinhardt and philosophers of science like Jim Baggott, argue that anthropic explanations are not real scientific explanations. They do not make sharp, unique predictions. They can accommodate almost any observed value of a constant after the fact. They shift physics from explaining why the universe has the constants it has to explaining why we observe the constants we do, which critics say is a fundamentally different and weaker task. This debate is not resolved. It sits at the intersection of physics, philosophy, and the question of what counts as a legitimate scientific explanation. Chapter 10: Quantum Computing and what it tells us about reality. Here is a concrete, practical angle that rarely appears in discussions of the quantum multiverse. Quantum computers exist. They work. And the reason they work, according to some of the physicists who build them, is that they are performing computations across many parallel branches of the wave function simultaneously. This is David Deutsch's argument, and Deutsch is not a marginal figure. He is one of the founders of quantum computing theory. A classical computer solves a problem by following one sequence of steps. A quantum computer can, in some sense, explore multiple computational paths at once. For specific types of problems, factoring large numbers, searching unsorted databases, simulating quantum systems, this provides an exponential speed-up. Shor's algorithm, which can factor large numbers exponentially faster than any known classical algorithm, was demonstrated on quantum hardware. Grover's algorithm provides a quadratic speed-up for search problems. These speed-ups are real, measured, and theoretically well understood. Deutsch argues, where is all that computation happening? If a quantum computer with thousands of qubits is solving a problem that would require more computational steps than there are atoms in the observable universe for a classical machine, that work is being done somewhere. In the many worlds picture, it is being done across an enormous number of branches, all computing in parallel, with the result emerging when they recombine through interference. Not every physicist accepts this as proof of many worlds. The alternative interpretations, Copenhagen, pilot wave, collapse models, also predict that quantum computers work, each for their own reasons. But the quantum computing argument makes many worlds less abstract. It ties the philosophical question to technology that sits in labs in Mountain View and Zurich and Cambridge today. Chapter 11. The decoherence timescales. How fast does a universe split? One of the most concrete, testable aspects of the many worlds picture is decoherence, and the timescales involved are almost impossible to comprehend. A single isolated electron can maintain quantum superposition essentially indefinitely. Its decoherence timescale in a vacuum is extremely long. But the moment a quantum system interacts with its environment, decoherence sets in with extraordinary speed. A dust particle, about a micrometer across, containing roughly 10 billion atoms, immersed in air at room temperature, decoheres in approximately 10 to the power of minus 31 seconds. That is 20 orders of magnitude faster than any time scale accessible to any measurement. A cat-sized object decoheres so rapidly that the time scale is not meaningfully expressible in any human units. This is why we never see macroscopic objects in superposition. Not because superposition stops applying at large scales, the mathematics gives no reason for it to stop, but because environmental interaction makes the branches permanently inaccessible to each other faster than any physical process could exploit the interference. This has a practical implication for quantum computing. Quantum computers must work extremely hard to isolate their qubits from the environment. Superconducting qubits, the kind used by IBM and Google, operate at temperatures near absolute zero, about 15 millikelvin, colder than outer space, specifically to minimize thermal decoherence. Even so, decoherence limits the time qubits can maintain quantum states to microseconds or milliseconds before errors accumulate. Quantum error correction, one of the most active areas of current quantum computing research, is essentially the art of fighting decoherence at scale. This is physics operating in direct contact with the mathematics of quantum branching. Every error-corrected quantum computation is, in a very real sense, a practical experiment in the behavior of quantum superposition at non-trivial scales. Chapter 12. What physicists actually believe. It is worth pausing here to take the temperature of the physics community. Not because scientific consensus determines truth, it does not, and the history of science is full of correct minority views, but because the distribution of expert opinion reveals something about the actual epistemic state of the question. In 2011, philosopher of physics David Chalmers conducted an informal survey at a Quantum Foundations conference. The survey results were illuminating. Many worlds and Copenhagen each had significant pluralities of support, with no single interpretation commanding a majority. A more systematic poll of physicists and philosophers attending the Quantum Physics and the Nature of Reality conference in 2011 found that about 42% favoured Copenhagen, 18% favoured many worlds, and the rest were distributed among other interpretations or expressed no preference. But these surveys sample a specific community, Quantum Foundation's researchers, who are not representative of physicists generally. Most working physicists do not have strong opinions about interpretation. They use quantum mechanics, it works, and they do not find the foundational questions necessary for their day-to-day calculations. Among physicists who have thought seriously about interpretation, many worlds has gained ground substantially since the 1990s. Prominent advocates include David Deutsch at Oxford, Sean Carroll at Johns Hopkins, Max Tegmark at MIT, and David Wallace at the University of Southern California. Prominent skeptics include physicists like Roger Penrose, who believes the collapse must involve a new physical mechanism related to gravity, and Lee Smolin, who considers many worlds to be insufficiently explanatory about what distinguishes branches. The honest state of affairs is, no interpretation is universally accepted, no interpretation has been empirically confirmed over its competitors, and the question remains genuinely open. Chapter 13, The Geometry of Branching. How many worlds is too many? A question that sounds naive, but is actually profound. How many branches are there? In the naive picture, the popular image, every quantum event splits the universe into two. Two slits, two branches. A radioactive atom either decays or it doesn't. Two branches. This is not quite right. Quantum states are described by a continuous mathematical object, the wave function, that lives in a space called Hilbert space. When decoherence occurs and branches form, the number of resulting branches is not two. It is an enormous and arguably infinite number, weighted by the quantum amplitudes. The branching is not like a tree that forks cleanly. It is more like a continuous smearing of possibilities, with structure that depends on the specific physics of each interaction. This makes the counting of worlds conceptually subtle. Physicist David Wallace argues that asking how many worlds are there is like asking how many waves are there in the ocean. The question implies a discreteness that does not actually exist in the underlying physics. The branches are emergent, approximate structures, like tables and chairs, are emergent from atomic physics, not fundamental ontological entities. This perspective is important because it deflects a common objection, that many worlds is extravagant in its ontology, constantly generating vast numbers of real universes. Wallace's response is that many worlds does not add entities to the ontology. It takes the quantum wave function, which every quantum theory needs anyway, and says it is the whole story. No collapse mechanism, no hidden variables, no new physics, just the wave function, evolving according to the Schrödinger equation, all the time. The many worlds are already in the mathematics of standard quantum mechanics. The only question is whether you take that mathematics literally. Chapter 14. The Signature of Another Universe. What would proof look like? This is the chapter that separates philosophy from science. What would it actually take to confirm or deny the existence of quantum parallel universes? The honest answer involves distinguishing between different types of evidence. For the inflationary multiverse, we discussed bubble collision signatures. For the quantum multiverse, many worlds, the situation is more subtle and more contested. One claim is that many worlds is unfalsifiable, since the other branches are permanently inaccessible by decoherence. There is no way to detect them. If that is true, many worlds is metaphysics, not physics. This is a serious objection, and it is made by serious people. But there is a counter-argument. Decoherence is not mysterious or unverifiable. It is a precisely calculable quantum mechanical process. If you could construct a quantum interference experiment involving extremely large objects, approaching macroscopic scales, and verify that interference still occurs according to the Schrödinger equation at those scales, that would provide evidence against objective collapse theories. It would not directly confirm many worlds, but it would eliminate the primary competitor that claims the Schrödinger equation breaks down. Experiments testing quantum superposition at progressively larger scales are actively ongoing. In 2019, a team at Delft demonstrated quantum entanglement between two macroscopic diamond objects separated by about 2 millimeters, not huge by everyday standards, but enormous in quantum terms. In 2020, researchers created quantum superpositions involving molecules containing up to 2,000 atoms, the largest mass objects ever placed in verified superposition. The direction of travel in experimental quantum mechanics is toward larger and larger quantum systems. If at some scale the Schrödinger equation fails, if superpositions spontaneously collapse in a way not predicted by standard quantum mechanics, that would be strong evidence for objective collapse models and against both Copenhagen and many worlds. If superposition persists at all scales tested, that supports the mathematical foundation of many worlds, even if it does not clinch it. There is also a more exotic proposal. Physicist Adrian Kent has suggested that if an observer could somehow survive the experience of quantum suicide, a grim thought experiment where you repeatedly expose yourself to a quantum event that could kill you, and always find themselves surviving, that would be evidence for many worlds specifically. This is not a feasible experimental proposal. It is mentioned to illustrate the logical structure of what evidential support for many worlds would look like from the inside. The practical experimental frontier is large-scale superposition and precision tests of the Schrödinger equation. These experiments will not confirm many worlds, but they can narrow the space of viable alternatives. Chapter 15. The Role of Information in Quantum Reality. There is another angle on this question that has gained significant traction in the past 2 decades. It comes from combining quantum mechanics with information theory. John Archibald Wheeler, one of the most influential physicists of the 20th century, who coined the terms black hole and quantum foam, spent his later career arguing for a position he called it from bit. The idea, at the deepest level, physical reality is not made of matter or energy. It is made of information. Every physical quantity, every particle, every field, every space-time event derives its existence from the answers to binary questions, from bits. This is not a fringe view. The field of quantum information science, which has grown enormously since the 1990s, treats quantum states fundamentally as information-carrying entities. The information-theoretic perspective on the measurement problem is called quantum Bayesianism, or QB-ism, developed by physicists Christopher Fuchs and Rüdiger Schack. QB-ism's position is radical. The wave function does not describe the physical state of the world. It describes an agent's beliefs about the outcomes of future experiments. Collapse is not a physical event. It is a Bayesian update, the same thing that happens when you revise your beliefs after learning new information. In this view, there is no measurement problem, because the wave function was never a description of external reality to begin with. QB-ism explicitly denies that quantum mechanics tells us anything about what is really happening between measurements. This is the furthest possible departure from many worlds. Where many worlds says everything in the wave function is real, QB-ism says the wave function is not even trying to describe reality. Both positions take quantum mechanics seriously. Both are held by smart, careful physicists. And this is the core of why the question in the title of this documentary does not yet have a clean answer. It is not just an empirical question about what experiments find. It is tangled with deep questions about what physics is supposed to do and what real means. Chapter 16. Quantum Gravity, the frontier where everything breaks down. There is one more layer to this story. Everything we have discussed, quantum mechanics, decoherence, many worlds, interpretations, applies to quantum mechanics as it currently exists. But quantum mechanics as it currently exists has a problem. It is incompatible with general relativity. General relativity, Einstein's theory of gravity, is our most accurate description of space, time, and the large-scale structure of the universe. Quantum mechanics is our most accurate description of particles, fields, and the small-scale structure of matter. Both are extraordinarily well confirmed by experiments, and they cannot both be exactly right. The equations of general relativity treat space and time as a smooth, continuous structure. Quantum mechanics treats fields as made of discrete units and fills empty space with fluctuating energy, quantum foam. These two pictures are irreconcilable with current mathematics at extreme conditions, inside black holes, at the Big Bang, at the Planck scale of about 10 to the power of minus 35 meters. The search for a theory of quantum gravity, a framework that unifies both, is the deepest open problem in fundamental physics. String theory is one candidate. Loop quantum gravity is another. Causal set theory is a third. None is confirmed. Here is why this matters for the multiverse question. Several proposals for quantum gravity suggest that the wave function of the universe, the quantum state of everything that exists, does not evolve in time in the usual sense. In canonical quantum gravity, There is an equation called the Wheeler-DeWitt equation. It describes the quantum state of the universe, and time in that equation is absent. The equation is static. Time, in this view, is not a fundamental feature of reality. It is an emergent phenomenon, arising from the internal structure of the universal wave function when observed from within. This connects to a picture developed by physicists including Bryce DeWitt, James Hartle, and Stephen Hawking, in which the entire history of the universe is encoded in a single quantum state, with no external observer, no collapse, and no measurement problem of the usual kind. The multiverse question in this context is not just about parallel branches of quantum events. It is about the quantum structure of space and time itself, and we do not yet have the mathematics to answer it fully. Chapter 17. The Philosophical Stakes. We need to be honest about what is at stake in this question beyond the physics. If many worlds is correct, the implications for how we understand ourselves are significant. Every choice you make, every moment where quantum events influence the firing of neurons in your brain, or the mutation of a cell, or the path of a photon that affected the chemical reaction that led to a particular thought. Branches. In the many worlds picture, there is no single version of your life. There is an enormous number of versions, all equally real, diverging at every quantum fork. The version of you that made a different choice last year exists in a branch that has been inaccessible to you since the moment of branching. This does not mean your choices are meaningless. Within your branch, your choices determine the future of your branch. The fact that another branch exists does not affect what happens to you. But it does affect certain questions about identity, responsibility, and uniqueness that philosophers have been grappling with since Everett's thesis. Derek Parfit's work on personal identity, specifically his arguments about what matters in survival, resonates deeply with the many worlds picture. Parfit argued that identity across time is not what we normally think it is. What matters is psychological continuity and connectedness, not some mysterious fact of being the same person. In a branching universe, both successors of a branching person are continuous with the original. Neither has a stronger claim to being the real continuation. These are not idle philosophical puzzles. They bear on how we think about decision-making under quantum indeterminacy, and on what it means for an action to have a single outcome. We raise them not to resolve them, but because any serious account of the quantum multiverse must, at some point, reckon with them. Chapter 18. The Current State. What we know and what we don't let us take stock. Here is what we actually know. Quantum mechanics works. Its predictions are confirmed to a precision unmatched by any other physical theory. The measurement problem is real. Quantum mechanics, as standardly formulated, does not give a complete account of how definite outcomes emerge from superpositions. This is not a fringe opinion. It is widely acknowledged by physicists who work on foundations. Decoherence is real and well understood. It explains in quantitative detail why macroscopic superpositions are never observed. It does not, by itself, solve the measurement problem, but it clarifies the structure of the problem significantly. Multiple interpretations of quantum mechanics are mathematically consistent and make identical predictions for all experiments performed so far. The inflationary multiverse is a consequence of the leading theory of the early universe. Inflation is well supported. Eternal inflation, which implies bubble universes, is a theoretical extrapolation that has not been confirmed or ruled out. The string landscape is a feature of string theory. String theory itself has not been confirmed experimentally. Here is what we do not know. We do not know whether the wave function is a complete description of physical reality or a calculational tool. We do not know whether the Schrödinger equation holds at all scales or breaks down at some level. We do not know whether the inflationary multiverse is real. We do not know whether parallel branches of the quantum wave function are real in the same sense as the branch we inhabit. We do not have a confirmed theory of quantum gravity. We do not know whether the constants of physics are fixed or vary across a multiverse. This is the honest picture. The question in the title of this documentary, "Do quantum universes really exist?" does not have a confirmed answer. It has a mathematical framework that makes the answer possibly yes a serious scientific position. It has experimental frontiers that are slowly tightening the constraints. And it has a conceptual puzzle at its heart, the measurement problem, that has been with physics for nearly a century and shows no sign of clean resolution. Conclusion. Physics has a history of proposals that sounded absurd and turned out to be correct. The Earth moves through space. The universe had a beginning. Space is curved by mass. Time passes at different rates depending on velocity. Every one of these was once considered outrageous. Every one is now standard confirmed physics. The possibility of parallel universes is not in the same evidential position as those. We have mathematical arguments, we have theoretical frameworks, we have inference from the behavior of quantum systems that we can actually measure. We do not have a confirmed detection. But the standard of evidence matters here. When physicists say quantum universes might be real, they are not saying it because the idea is exciting. They are saying it because the best mathematical description of physical reality, tested more precisely than any other theory in science, appears, when taken at face value, to require them. The universe is not obligated to match our intuitions about what is reasonable. It was not built for us. And the deepest discoveries in physics have almost always been the ones that demanded we rethink what real means. Whether or not parallel universes exist, the question forces us to ask something more fundamental. When we say something exists, when we say it is real, what do we actually mean? And is the answer to that question something physics can give us? Or does it require something more? We do not know. And that is exactly why the question is worth asking.